Okay, so in this task, the situation is that we want to build a cement ramp, and this is showing the ramp here that is going down and going up, and this is the ground level. That is 6 feet wide and 8 feet long, and under the entire ramp has to be at least 4 inches deep. So notice at the ground level it's dug down into the ground, where up here it doesn't need to be. So the first question is, how much material do we need? And because this is done to scale, where 1 centimeter is 1 foot, we can measure length times width times height, or calculate it, or we can measure the front and multiply and very easily get 16 cubic feet, or we could just know length times width times height. The second question is, what angle would you need in order to construct this ramp? So we're looking at the angle here, which in order to do this problem, students would need to know about tangent and trigonometric functions in a right triangle from at least their geometry class. So they would say tangent of the angle equals opposite over adjacent. So then they could tell you that the opposite of the angle would be 4 inches, which would be 1/3 of a foot. The adjacent side would be 8 feet. And then they could put that in their calculator. They could do inverse tangent, and they could figure out the angle to be 2.38 degrees. So they could use their pencil and paper geometry, or they could just look at the angle. Or they could do any combination of those to reinforce it. So that's not necessarily showing how this is the dynamic capability, though, that I really want to get at. The next question is going to be showing how the angle, when you change the angle, compares to the shape and compares to the volume. So you can kind of simultaneously show the things that are changing and the relationship, which is what makes this dynamic software really nice. Okay, so the third question is, we want to increase the angle in order to prevent standing water from ponding when it rains. So notice we contextualize this and put it in a real-life situation. So when we do this, the side that is underground will stay 4 inches buried because there's no reason to change it, but the side that is above ground will change in height. So if we use an angle of 5 degrees, how high above ground will the side be? So we could just push the button and watch it grow until we're at 5 degrees. And I'm going to get exactly 5 by doing that. So, and we could just measure the length of that side. Remember, this is 0.70 feet, so you can multiply by 12 if you wanted inches, and you could discuss the unit conversion. The other thing you could do is obviously use that tangent function again, opposite over adjacent, and you could discuss doing that on paper. You can compare the answers, and it kind of gives students a nice verification for what they're doing. How much material would we use? Same thing. You could do length times width times height, or you could look at the volume. Okay, so you could do the same thing for 7 degrees. So here's 7 degrees. You could measure or calculate your height. You can measure or calculate your volume. If the angle is changed to D degrees, now we have to do a little bit more thinking. So this is really extending this to algebraic thinking about an expression now. So we could continue to watch the volume and the side change, and that may or may not help us to determine whether there's a pattern. One of the things that we might try to do is we might try to graph the relationship between the angle and either the side or the volume, but for now I'm going to do the volume. So we could plot as XY. And I'm going to go ahead and trace the plotted point. Now, one of the limitations on this program is, or by using this type of a system to solve this problem, is that we know the answer actually depends on tangent, and tangent's not a linear function. However, as it relates to this problem, because you're so zoomed in, it actually appears to be linear. So there you see the angle and the volume changing, angle being the x-coordinate, volume being the y, as I animate the angle parameter. So while this may be a limitation for some students if we're trying to discuss the trigonometric ratios and how the angles relate, this would also serve to be a good talking point in somewhere like a calculus class where you can discuss local linearization, where if you're really zoomed in on this particular function, it actually looks linear and we can approximate and interpolate using a line. So here's my equation of, here's my line, and one of the nice things you could do, you could either pick two different points, for example, 4.03 comma 21.53, and then you could pick another point the same way, or you could just make a point on the line and make another point and connect the dot to the line, and that looks like it could probably move just a little bit and be a little bit nicer. There we go. That's not it. Okay. And what you can do is you can actually just measure the equation of line. And then you have a nice model in context for something that you can talk about. So what happens with the 3.36? What does that represent? What does the 8.02 represent? And obviously the 8 would be the height if we had 0 degrees. So that makes getting at the concept of the modeling a little bit easier because you don't have to go through all of the higher level math skills that you might not have until geometry or later to do something like look at the equation of a line or to look at the way that angles change with the way volume changes.